Hello, so we are going to go ahead and go straight into zero force members under trusses. So previous video I went through the method of joints and we talked about how trusses are made up of slender members that are joined together at pins. Now sometimes a truss is made up of very many slender members, so what you want to do in order to start analyzing and figuring out what's going on the inside, whether the member is in tension or compression, is to try to figure out which members are really not going through anything right now and are in basic equilibrium when they are at rest. So for example, one of the things that we want to look at is zero force members, and what those are, for example, is if you have two members that are non-collinear, and what that means is that those two members are not acting in the same line or in the same straight line, and there are no external loads at that pin or joint, then the two members are zero force members. So I'm going to go ahead and highlight what I mean for this problem. So for the problem that we have over here, if you're looking at the definition, two members are non-collinear and there are no external loads. So this is non-collinear, this is non-collinear, which means that these two, if there's no external force at D, then these two, which is DE, FDE, and FDC, are both zero force members. So we can go ahead and cancel these two out. In the same way, if we look at the corner at A, you will see that these two members are non-collinear, as you can see, because they are not in the same line and do not act in the same path, and there's no external load at A, F, AF, and FAB are both zero, which means that AF and AB are zero force members. So you can represent the same truss below with just FE, C, and B as joints. That really simplifies when you're trying to come up with a solution of what's going on inside each member. Another rule for zero force members is what we have right here, and that is at a joint, if three members meet at a joint with two of them being collinear, and what collinear means in this case is when the two members lie in the same path and there are no external reactions or supports, then the non-collinear member is a zero force member. So let's go ahead and put that in practice. So we have at joint C, we have CB, CD, and AC. Now you see that CB and CD are collinear because they're in the same line, and since there's no external force at joint C, it tells us that FAC, the force inside AC, is equal to 0. So you can go ahead and eliminate FAC. In the same way, looking at DE, DC, and DA, once again, DE and DC are collinear with no external force at D. It tells us that AD or FAD is equal to 0. Okay, so we can represent the same truss that you're seeing up here down here below, and that's just going to be a simple three-member truss with an external load on there. So that's as simple as how zero force members are. Okay, so two rules: two members are non-collinear, no external load, it means that both of them are zero force members. Three members meet at a joint, two of them are collinear, no external load, then the non-collinear one, which is what we have right here, are the zero force members. Okay, in the same way, if we have four members, AC, CD, CB, and CE, meeting at a cross, you can easily justify that FAC is equal to FBC and FCE is equal to FCD. Okay, so that's a special condition. Another special condition is this. If you're looking at this, you can notice that FAD is equal to FAB because they're meeting in the line, which tells us that FAC is taking up all of the external load, which is at P. So then FAD is equal to FAB and FAC is equal to P. If there's no external load, then where P is equal to 0, then FAC equals 0, which tells us that FAC or AC is a zero force member.